Hello guys, a very happy good evening to everyone of you. And guys, now we are just going to start the next series in production engineering. Okay, so in the before time I just explained to you each and everything detailed about the production engineering. So what are the things in the production engineering I just explained to you. Okay, so it means each and every point of it means especially the formulas I just told in an elaborate way. I think so especially you got a lot of point of view and different point of view and how each and everything is been working. So now we'll just been starting the next class. Okay, so next class is so much simple only, so no need to just confuse or no need to just get triggered as well. So just a simple equation and just a simple calculation it has been given in this kind of questions. Okay, so as soon as possible we will try to cover the entire thing. Okay, so then without wasting time let us get started. Okay, so here mostly basic things only will be there. Okay, okay, so it means analysis of metal cutting. So guys, in before times until now we haven't seen any kind of force. We have just seen only the angles, the velocities, cutting velocity, chip velocity, the angles and the which and everything. But now this entire chapter will be just seeing upon the analysis of metal cutting, means how much the force will be and how much each and everything will be. So we are just especially going to see about this. Okay, so I think so you can see this is a metal and this is chip is moving like this. Okay, this one and like this it will be. So you can see the downward the force is given as thrust force. Okay, this side force will be cutting force. Okay, I think so I got it. These two things are the most important thing. Okay, horizontal component generally causes cutting force and the vertical component generally goes for thrust force in a downward direction. Okay, so no need to confuse yourself. Okay, so especially how to say, I mean these are the other kind of things you can see in this. They have asking the cutting force, radial force, normal force and shear force. Further I'll just explain to you, because in the before class I just explained to you how the force will be and what are the interaction will be. I just explained to you. So where is this one? There. So it means these are the three different types of thing I just explained to you. Okay, wait just 1 second. So you can see in this normal thing the thrust force will be acting upon this. Okay, because the thrust force leads to the contact between the tool as well as the workpiece. So this is the most important thing, used to contact. Okay, used to contact, and cutting force also is in between the tool as well as the workpiece, but it will just cut because the thrust force is generally a holding force and the cutting force used to cut the entire material. Okay, but thrust force will be acting in a different direction as well as the cutting force will be acting in a different direction. Okay, I think so you can see. So the thrust force will be acting with this, the cutting force will be acting upon this. Okay, I think so you can understand. So this is two forces. Okay, the next force is friction. You can see the it means next force is shear. Okay, whenever there is a shear pain, I think I just explained. So it means there will be a shear pain. It means angle of theta. I think so. So in the shear pain also shear force will occur. Okay, you can see the shear force will be occurring in this direction. Okay, shear pain is this means the shear force will be occurring, and it means against to that the normal shear force will also occur. Okay, so here also two forces came. It means shear force as well as normal force. The next thing is you can see where is my blue pen. So next thing is tool chip interface. Okay, in this thing friction force will be there. Okay, you can see in the while the chip moves out, you can see the frictional force will be there. For the friction also the normal force will be there. So here two force, here two force, here totally 6 forces will be there. Okay, so according to that we will just draw a diagram. Okay, so I think so you can understand. So like this we will just tilt the thing and we will just draw each and everything. Okay, in this diagram I just explained before, like this the circle will be, you can see especially the angle will be like this. So this is the alpha. So this especially this one will be the frictional force, okay, of the tool, and this one will be the normal force. Okay, so next thing which will be the cutting force, FC, cutting force, and this one will be the thrust force, FT. Okay, and after that it means shear force will be the shear force, F of S, and normal shear force will be like this. Okay, and next one from here to here the radius will be. Okay, I think so got the point. It means for the frictional force, it means for the radius to normal it is the beta. Okay, just a simple thing. For this one it will be the shear angle, and this one will be the, this one is since this is alpha, you can see this thing and this thing will be same. Okay, this thing and this thing will be same like this. Okay, you can see this also will be the alpha. Okay, so this entire thing is a 90 degree. Okay, and this way you are getting the point. Okay, so you can see this is beta minus of alpha degree. Okay, this is beta minus of alpha degree. This one will be 90 minus beta minus of alpha. Okay, just a simple thing, just to keep in your mind, that's it. Okay, so it's 90 degree and 90 degree minus of beta minus of alpha. This one will be minus alpha. Okay, okay, so we'll be seeing the next thing. Okay, so here each and everything is being represented in different way format, that's it. Okay, so not a bigger complicated thing, just a simple thing. Okay, so now we'll be just seeing the little bit of other thing, kind of thing here. Okay, so you can see here it has been asked in the ESC 2000. Okay, so the first thing what they have just given. So guys, literally for the most of the thing we need to find the radius. So after calculating the radius only, we need to just go for the other thing. Okay, so first we need to find the radius of the entire thing. Okay, so you can see rake angle is given alpha. Alpha is 10 degree and chip thickness ratio R is 0.35 and uncut chip thickness. Okay, uncut. So T. So TC we don't know, that uncut chip thickness 0.51. Width of cut. Width is 3 millimeter. Shear stress is 285 Newton per mm square. Okay, shear stress tau. Okay, so new, it means they have just given the mean coefficient of friction equal to 0.65. Okay, they are asking the cutting force, radial force and normal force and shear force. Okay, so cutting force, how we can just find it. Okay, so as I just told you that diagram you should draw. So this is the cutting force, this is the thrust force, this will be the radius. Okay, this will be the shear force Fs, this will be the normal force, this will be the friction F, and this will be the normal. Okay, so this one will be the alpha, this one will be also alpha, this one will be the shear angle, this one will be, you can see this is beta. So this entire thing will be beta minus of alpha. Okay, so you can see this entire thing is 90 degree. Okay, so in this 90 degree equal to this one beta minus of alpha, so this one plus of alpha plus of x. Okay, so okay, you can see this alpha as well, guys. So 90 minus of beta equal to x. Okay, so this entire thing is 90 minus of beta. Okay, so what they are calculating, FC. So this is FC. So how we can just calculate FC? So each and everything, the radius is so much important. So first we need to calculate the radius. Okay, so in the before, it means in the before thing I just explained each and everything. Okay, so how we can calculate the radius? Okay, so they have just given shear stress. Okay, so since shear stress is given, so shear force equal to shear stress into area. So shear stress in the question is given, so shear stress into which one, area. So W T1 divided by sine of theta. Okay, so I just explained it. So first we will see this question. I think so, they page number 20. See, for this one, so sine theta. Okay, sine of the shear angle. So we know the shear angle? No, we don't know the shear angle. So what will the tan of shear angle equal to R of cos alpha divided by 1 minus of R of sine alpha. Okay, alpha we know, alpha is how much, 10 degree. So put here and calculate the, it means shear angle we just calculate and make it sure it is being placed in here. Okay, so next what will be the T1, just think. Okay, the uncut chip thickness. Okay, so you can see this one is a T1. Okay, so make sure Fs is equal to tau shear stress. They would have given shear stress into, it means width of the cut is given 3 mm, 3 millimeter, so into 0.51 millimeter divided by sine of the theta. It means this angle will be 20 degree. Okay, calculate the shear force we just got. Okay, now you can see guys Fs. So it means I'll just draw the diagram. This is Fs, this is normal, this is radius. Okay, so what is the angle between this one? So you can see this one is this shear angle, this one is beta minus of alpha. So it means the opposite. This one is adjacent, this is hypotenuse. Okay, so what will be the thing? So we need to calculate the radius. Means definitely sine is, suppose sine theta equal to opposite divided by radius. Okay, but it won't come. So cos theta equal to adjacent divided by hypotenuse. Okay, cos theta is also on the same thing, cos shear angle plus of beta minus of alpha equal to this opposite is Ft, shear force divided by radius. Okay, so radius equal to Fs divided by cos of shear angle is how much? 20 degree. So beta is, B is how much? We literally don't know, but they have given coefficient of friction. Okay, so tan, so nu equal to tan of B. Okay, okay, so they have given new angle. Okay, so tan inverse 0.65 equal to beta. Okay, beta value is 33. Okay, now plus of 33 minus of 10 degree. Okay, Fs we would have known by calculating this one, you can just calculate Fs. So now we have just calculated the radius. Okay, okay, this is the radial force, entire thing, this is the radial force. Okay, radial force acts in a radius direction. Okay, so now it is so much easier to calculate remaining thing. Okay, suppose Fc means, you can see Fc, this one is Ft, this one is the radius, this one is beta minus of alpha. So they have calculated this opposite, adjacent, hypotenuse. So beta minus alpha means how we can just find? Sine cos only. So cos theta equal to Fc divided by hypotenuse radius. Okay, so Fc equal to cos beta minus of alpha into of radius. Okay, radius of radial force, just calculate this and put here, and cos beta is, I guess you don't know this thing, alpha is 10 degree, put and calculate Fc. Okay, that's it. Okay, okay, suppose if they asked about a normal force, means you can see this is normal force, so just calculate this one, we will get the entire normal force, or the normal force might be, we can just try upon this one. Okay, this one you just calculate, we will get the normal force, and the shear force I just already explained to you. Okay, so the next thing, what is the main thing is, wait, I'll just turn the paper. See, and the thing is given is orthogonal cutting. Okay, so that was I was thinking. So orthogonal cutting means generally the which force, the radial force won't be. Okay, so I think you can understand. So you can see this one, where you can see this one, radial force F of y equal to 0, because the force is present in turning, not in orthogonal turning. Okay, so I think so you got the point. So we can just see the next question. So you can see this one, it means the Mershon force circle diagram is completely valid for only for orthogonal cutting. Okay, do not compare with the orthogonal turning or oblique cutting. Okay, only valid for 2-dimension orthogonal cutting. Okay, by the ratio of F and N, it means it gives coefficient of friction. Okay, it means the friction force along with the normal friction force, it gives the ratio of the coefficient of friction, how the friction will be acting like that, will just. Okay, I think you got the point. Suppose in case of if alpha equal to 0, each and everything will become as a square. I'll just explain this one to you later on. Okay, so here it will be there. Okay, so you can see here what is done during measuring, if the inclination angle is 0 and it means the side cutting angle will also become 0. Okay, You can see this is pure orthogonal. Okay, whenever the alpha is 0, it becomes as pure orthogonal cutting. Okay, just a simple thing. So while like this kind of thing is been occur, the entire angle will be where one. You can see this one. So you can see this f, this one. So each and everything will be same. So cutting force will be equal to the normal force, and the friction force will be equal to the touch force. Here you can see shear force, and I think so you can understand. Just a simple thing, not going to complicate yourself. Okay, you can see this one. So you can see here orthogonal turning is given. Okay, in orthogonal cutting generally the thrust force will be 0. Okay, it means the radial force will be 0, but you can see here orthogonal cutting is given. Okay, orthogonal turning is given, that's it. Okay, so new, it means frictional force given 402.5 Newton. Frictional force is perpendicular to the cutting velocity vector. Okay, the feed velocity is negligible with respect to cutting velocity. The ratio of frictional force to the normal force, is 1. Okay, so you can see the friction force is directly, it means equal to n. So the normal force also will be the 402.5 Newton. Okay, the uncut chip thickness T 0.2, chip thickness is TC equal to 0.4. The cutting velocity VC equal to just VC means chip velocity 2 meter per second. Okay, so they're asking the shear force. So shear force F of S. So F of S is equal to shear stress into B into T1, it means breadth into T1 of sine of theta. Okay, so how we can calculate, because here alpha is given 0, so shear stress whether they have given good question guys, literally in my point of view. So what could be the answer? So you can see here F is given as, it means frictional force is equal to normal force. Okay, this friction force is equal to this normal force. Okay, so they are asking the Fs, this one they are calculating. Okay, oh yes, I thought, oh I was like, okay, really sorry. So let us go upon this one. Okay, so for example, where I can just start, I was thinking a little bit of this like a formula, but it's like you can see. So you can see F of S equal to, it means like it will be Fs, this one is it means normal shear, this one will be the entire thing. Okay, so opposite adjacent hypotenuse. So Fs, it means cos theta equal to shear force into radius. Okay, Fs equal to cos theta will be which one? Cos theta will be this one, shear angle plus of beta minus of alpha into of radius. Okay, first we need to find the radius. So after calculating radius, we can just find each and everything. So here theta calculation, so tan angle, shear angle equal to r cos alpha divided by minus of r of sin alpha. So r is what? 0.2 with respect to which one? 0.4. Okay, so 0.5 will become. Okay, r equal to 0.5. So put here, and alpha is 0 degree. Okay, just put here and calculate theta. So while you are calculating theta will be, it means shear angle will be 26 degree. Okay, so next thing you can see, since this one, so what will be the beta equal to tan inverse of tan of nu. Okay, wait. So same, so you can see tan beta equal to nu. Okay, nu equal to F divided by n. Okay, I think so you're getting by. So here the nu is given 1, so beta equal to 45 degree. Okay, I think so you're getting. So beta we just calculated 45 degree, it means this one we just calculate, this one over. Now we need to calculate the radius. Okay, what will be the r? So calculating of r, for that what they have just given, radius, this one is friction, this one is beta. Okay, so you can see opposite adjacent hypotenuse. So frictional force divided by radius equal to cos of this one beta. Okay, so radius is friction force how much, 402.5 Newton divided by cos of 45 degree equal to which one, this radius volt. So while we are just calculating, it will come a certain quantity as 569. Okay, so this radius, so go and put here, it means in the radius, and we will calculate the shear force. Okay, I think so you are getting the point. Okay, such a simple question, so it means no need to complicate yourself. Okay, so we will be seeing the next question. Mostly in this sector, it means a lot of questions only will come, guys. So but most of the questions will be so much interesting thing. Okay, so next we will be seeing the second question. You can see in orthogonal turning. Okay, in engineering it has been observed that a frictional force, okay, the friction force perpendicular cutting, okay, the friction, so the rate of each and everything is same, but they are asking the rate of heat generation in what are primary shear zone. Okay, heat generator. Okay, heat generator at a primary shear zone, is how much? So okay, so shear it means shear velocity is so much simple. It means you can see this is heat generation is generally watts. Okay, watt is joule per second. Okay, joule is written as Newton meter. So shear force into shear velocity, that's it. You take this equation and you just put here and you can calculate easily. Okay, cutting velocity they are given, and cos shear angle minus alpha if the shear velocity. Okay, each and everything is given, just put and multiply and we can calculate the entire thing. Okay, that's it. Okay, so we can just see the next question. So you can see in this given orthogonal. Oh, they are asking orthogonal rectangle. Okay, so orthogonal turning. Oh, you can see the cutting force is perpendicular to frictional force. Oh, wait, frictional force. Okay, then definitely orthogonal rectangle will be so much equal. Okay, you can see guys, orthogonal turning. Okay, main tangential cutting force is perpendicular to the frictional force. So Ft and which one? The friction force so much equal. So it is, since it is parallel, so alpha equal to 0. Okay, that's it. Simple thing only. Okay, it has been asked in gate. Okay, in orthogonal turning machine of 100 field, you can see orthogonal turning. Okay, so orthogonal cutting is T equal to depth of cut, T equal to f of sine lambda, and T equal to f of sine 90 degree. So these are the three angles you just want to keep remember in your mind. Okay, so that's given orthogonal turning. Okay, so T equal to f. Okay, that's it. Okay, depth of cut. Okay, cutting velocity. They are asking the normal force acting at the chip and tool. Okay, chip tool. Okay, so they are asking the which one, chip and tool means the friction force will be like this and the normal force will be like this. Okay, they are asking the normal force. Okay, how we can calculate, and what are the things they have given? They have been given the main tangential cutting force. So which one it will be? This one is the cutting force, this one is the thrust force. Okay, so guys, literally it means each and everything is different. Okay, they just ask the cutting force. What is the cutting force? Fc. Okay, so it means, sorry, they are asking the n. Okay, whether alpha is given, no. Okay, so how we can calculate this one? So calculate Fc with respect to the radius, calculate this, or based upon you can calculate this one. So this one will be, how it will be? Okay, just think of, so this one will be beta minus of alpha. So since alpha is not given, so what are the next required things we can just calculate? Yes, one of the good question, because you can see alpha is not given. So R equal to T by Tc, LC by L, VC by V, and 1 by H. So tan pi equal to r of cos all alpha minus r of sin alpha. Now this also is so much difficult to calculate. Okay. Just think it, guys. Think what could be the answer. Maybe they just implement it, you get a father formula. In my case scenario, I just think so. Okay, let us see. No problem. Okay. Om Namo Bhagavate Vasudevaya. Om Namo Bhagavate Vasudevaya. Oh, this question and this question is same. Okay. Sorry guys. So as since both of the question is same, you can see. Yes, the answer will be 1500. I just thought this is different question, this is the different question. Okay, I just haven't seen this one as two. So since both are same question, the answer will be 1500. That's it. Okay. So okay, we can just see about this one. It has been asking get 2015. A single point cutting tool with rake angle alpha equal to 0 degree. Orthogonal machining at a speed. Okay. Cutting speed equal to 180. Thrust for T f of t equal to 490. So power consumption. So power is generally force into velocity. Okay. So it is just represent watts. Okay. Okay. Force, it means cutting force into cutting velocity. Okay. So what is the cutting speed? Okay. Cutting speed is given 180 meter per minute. So convert to seconds, 60 seconds. So what is FC? So we have to just calculate the FC. Okay. Just it means same thing. FC, FD, radius R. Okay, since it is given the 0 degree, it means you can see this one frictional force, this one will be normal thing. Okay, so since it is given 490, so this is 490, it means FT is 490 equal to of F, it means friction force. Okay, so based upon this thing we need to calculate the radius. Okay, it's such a simple thing, so I'll just show it to you. You can see thrust force is equal to friction force. Okay, and you can see it the cutting force as well as the friction force will be perpendicular, not same angle. Okay, no need to confuse. Thrust force and normal force will be perpendicular but not same value. So for this we need to calculate the radius. Okay, so you can see this one is a beta minus of alpha. So it means what is a tan beta equal to nu. Okay, so nu, okay, beta equal to tan inverse of 0.7. Okay, just calculate and we can see the FC is so much easy, I think so. So FC equal to this one opposite other than this one is hypotenuse. FC divided by r equal to cos of beta minus of alpha. So what is the radius? Radius we can just calculate with respect to this one friction. Okay, this is what 90 minus of beta. So friction is how much? Simple, it means you can calculate with FT also. FT divided by this is sine hypotenuse. FT divided by which one? Radius equal to sine of beta. I think so. Beta is this one. Put here minus of alpha. Alpha is 0 degree. So FT equal to radius into, it means radius equal to sine of beta. Okay. Calculate the radius and just go and put the radius here. And FC we can calculate, and VC they have just given in the angle. So simple. That's it. Finished. They have just given the answer. Okay, so you can just go for this one. So coefficient of friction is this one, F divided by, so we have 6 divided by F by this one. The answer is D. That's it. So next one is merchant theory of or analysis. Okay, they are just given the merchant theory. So how generally the merchant theory will be there? We will be just seeing here. Okay, so you can see our theory of earnest and merchant. Okay, assumption the work material behaves like an ideal plastic. Okay, in this thing we just consider entire thing as ideal plastic. The theory involves minimum energy principle. Okay, this theory involves minimum energy principle. Just wait for 1 second. So Merchant theory of analysis, the work material behaves like ideal plastic. The theory involves minimum energy principle. Okay, no maximum and no maximum force. Nothing is maximum. Each and everything is minimum. At the minimum case, we are just seeing. And shear stress and beta are assumed to be constant and independent of pi. Okay, this merchant theory, it means like a easy representation. That's it. Okay, guys. It is based on single shear plane theory. We don't take only the primary shear plane. We just consider. We don't consider the secondary thing. Okay, the normal and the shear stress are distributed uniformly on the shear plane, but generally like this kind of thing won't occur. Okay, so you can see the deformation is only 2 dimension, only 3D cutting. Okay, so from merchant theory analysis, what is we just got is this thing. This is the main thing for calculation of the shear angle. Okay, shear angle equal to pi by 4 minus of alpha divided by 2, sorry, plus of alpha divided by 2 minus of beta divided by 2. Okay, shear angle equal to pi by 4 plus of alpha divided by 2 minus of beta divided by 2. Okay, this is the entire shear angle. Okay, so this thing might be represented 45 degree also, just a simple thing in according to your case scenario. Okay, so this pi by 4 we have just represented radian format. Okay, so you can see this was, suppose if you just tan shear angle of r cos like that, you just took mean, it will give the accurate. So this will give the approximate value. Okay, so you can see merchant theory use high shear plane angle means low shear plane is just low shear force. Okay, so merchant theory use high shear plane angle means smaller shear plane which has low shear force. Okay, this I'll just explain later on, and results low cutting force and power. And so since here each and everything will be so much lesser only. Okay, I think you got the point. So low cutting force, low power, low temperature, all will be easy for the machining. It means we are just going according to the machining process. Okay, such a simple thing. So you can see this one, merchant shear angle. So you can see merchant theory they have asked the value of shear angle. What is the thing? Pi equal to pi by 4 plus alpha divided by 2 minus of beta divided by 2, or 45 degree plus alpha divided by 2 minus of beta divided by 2 shear angle. Okay, so friction angle beta is 25, so alpha is 20 degree. Just put and calculate, that's it. So you can see in typical metal cutting operation, using the cutting, it means okay, the friction angle, the shear angle. Okay, so just go with the approximate value. Okay, you can see this approximate. So answer is 60 degree. Okay, so they have, okay, next question is this one. Okay, shear angle, cutting and thrust force. So cutting FC and FT they are asking. So each and every time what you have to just do is, you have to just make sure the F, it means the diagram. Okay, so what the things has been given, cutting speed, okay, V they just given, okay, rake angle given, okay, width of cut W equal to, which means B equal to 2, and uncut thickness D equal to 0.2, the average, okay, new they have shares they have given. Okay, shear angle, so simple. Okay, tan theta equal to r of cos alpha divided by 1 minus of r of sin alpha. So in this thing, what is r? So you can see everything, each and everything is not given. Oh wow, just think how we can just calculate. So you can see width of cut and uncut chip thickness given. Okay, average value, okay, new is given. Okay, so since they haven't given here r, how we can just calculate the shear angle? This one is Fs, this one is normal. It means, okay, this one is Fc, this one is Ft, and this one will be the F, this one is normal. Okay, so this one is a pi. Okay, you can see how we can calculate. This one will be the radius. Okay, so it means this one is, since this is Fs, this one is a normal, this one is the radius. You can see this entire thing is theta plus beta minus of alpha. Okay, so whether they have just given Fs, so shear stress tau they have just given. Okay, Bt sin of pi. Okay, shear angle only they are asking. Okay, shear stress, average coefficient of friction between two. Okay, 0.5. So based upon this one, it means we can just calculate beta equal to tan inverse of mu. Okay, this one beta angle we can calculate, alpha angle we can calculate, and both, but shear angle how we need to calculate? Okay, let us take approximate. Theta equal to what? 45 degree plus alpha divided by 2 minus of beta divided by 2. Okay, because here the r is difficult to calculate, so we can just take this answer. Okay, now we can calculate this one. Okay, based upon this we can calculate shear force, and just one thing, radius is we calculate means each and everything we can just calculate that. Okay, that's it. That's a simple question, no need to just get complicated. Okay, you can see. So just to calculate the radius. Okay, when you just calculate it means you can see the ways to calculate the radius, it is so much easy to find other things. Okay, that's it. So I think you have got the point. So most of the questions will be like this only, guys, so no need to confuse yourself. So you can see here, you can see especially in this sector lots and lot of problem is been accessed. Okay, so you can see how much important this entire thing will be. Okay, so now we will be seeing the next thing. Okay, tool wear. Okay, so for the next 10 minutes we will be just doing the tool wear. Okay, so you can see in tool wear, because generally while we are just making the tool to continuously load, so tool failure also occur. Okay, tool failure is two types. Okay, slow death, it means generally I'll just zoom a little bit. Okay, so okay, slow death means the gradual and progressive wear away of rake face, creator or the flank. Okay, generally it means in the rake face or the flank surface, the cutting tool, it means generally the wear will occur. Okay, you can see what is this one. This one is the rake face, this one is the flank. Okay, you can see this one will be a nose radius. Okay, I think so I got the point. So sudden death, it means a failure leading to premature end of the, suddenly it will occur. The sudden death type tool failure is difficult to predict. Yes, definitely. Tool failure mechanism, plastic deformation. Yes, while we are just mentioning, huge amount of heat will be there, and plastic deformation occur, brittle fracture may occur, fatigue fracture, edge also will, it means the cutting nose will be just chips away, so it is so much difficult. However, it is difficult to predict which, it means which of these process will dominate and where the tool failure also. Okay, so the next thing you can see, the fatigue failure of a tool is due to which one? Chip break and no variable thermos. Abrasive cutting, variable thermos, chip breaking, variable. So in my point of view, I think so it's B. Okay, B. So okay. So you can see tool wear. Tool wear generally comes under the category of flank wear, crater wear, chipping edge of the cutting edge. Okay, so literally. So you can see here generally flank wears occurs at the relief phase of the tool. Okay, rake phase and relief phase also there, but generally you can see in the relief phase only most of the tool wear will tend to occur. Okay, you can see this is flank wear. Okay, just a simple thing, no need to confuse. So flank wear occurs mainly in which of the following? No strip and it means front relief phase and side relief phase. Entire relief phase only the flank wear is still occur. Okay, action tool wear is expressed in the form of flank wear rather than crater wear. Yes, flank wear only we need to consider instead of mentioning the crater wear. So measurement of flank wear is simple. No, it's measurement of flank wear, but it's not. It more accurate means is not there. But answer will be B. Both are correct, but R is not correct position of A. Okay, that's one. You can see flank wear. So due to the flank wear only, it means the tool tends to just break off. Okay, you can see reason: abrasive by hard particles and inclusion in the workpiece, and shearing of microwaves, especially while it means I think so you don't know about the build-up pitch. So during the build-up pitch suddenly breaks off, and due to that lot of amount of flank wear will tend to occur. And abrasive by fragments of build-up pitch, you can see build-up pitch poking against the clearance face of the flank. At a low speed flank wear predominates. Okay, low speed also, and if metal removal rate increase, the flank wear also increased. Okay, one is abrasive by the hard particles, inclusion in the workpiece. Okay, so you can see in flank wear the cutting tool is much harder than the workpiece. Okay, yet the tool wear occurs due to the tool work interaction, because yet the tool wear occurs. Extra hardness is imparted on the workpiece due to the coolant use. No, oxides layers. Yes, oxide, it means oxides will definitely be there, but definitely extra hardness is due to coolant used is not okay. So extra oxides layer is definitely. So next one, extra hardness is imparted to the workpiece due to severe rate of strain. Okay, strain hardening. Oh yes, correctly guys, because we just travel towards the plastic deformation. In the plastic deformation, straight knurling is so much important. So during that time, this kind of thing will occur. Okay, vibration is induced in the machine tool. Due to the vibration also, certain kind of thing will occur. Okay, so answer is B, C, D, but in this most predominantly C is the 100% answer. Okay, so if they ask the multiple select question, means B, C, D will be there, but C will be the, it means how to say, means C will be the 100% correct answer. If they ask only one question, it's one answer. Okay, so direction you can see flank wear or wear length. Okay, effect flank wear directly affords the component dimensions to yes. Flank wear is usually most common determinant of the tool life. Okay, yes, definitely. So next one, flank wear, it is consist of three stages: primary, secondary, and tertiary. You can see primary is a minimum thing, but the secondary is a so much huge, and tertiary is a so much thing. Okay, so you can see in flank wear means primary region, the region where the sharp cutting edge is quickly broken down and finite wear land is established, quickly broken down. The secondary wear, you can see the region where the wear progresses at uniform rate, so it will be increased slowly. The tertiary region, the region where the wear progresses at gradually increasing. Okay, in tertiary region, the wear of the cutting tool has become sensitive to the increased tool temperature due to, so in the tertiary wear, due to the temperature only it fails. Okay, re-grinding is recommended before entering in. That's it. Okay, I think so I got the point. So okay guys, then that's it for this today's video, and let me see you in the next one. Until then, take care, bye bye, have a good day.